Okay, I think I'm going to get started now. So my name is Brian Kingsbury. I'm with IBM Research in Yorktown Heights, New York. And what I'm going to give you is really a whirlwind tour of automatic speech recognition. 80 minutes is really not enough time to cover the topic in detail. Some colleagues of mine, for example, gave a course on automatic speech recognition at Columbia University a couple years ago, and they took an entire semester. So what you're going to get is a picture of how a speech recognition system is put together, what some of the main algorithms are, but I'm not going to go into a significant amount of detail on any of the algorithms because there simply isn't enough time. I'm really relying on Jason Eisner to have covered, say, the forward, backward, and Viterbi algorithms in the context of discrete HMMs. And so I'm not really going to touch on those except to assume that you have enough familiarity to have some idea of how they're used as building blocks for putting together a speech recognition system. Similarly, I'm relying on Hynek to have covered a lot of the details on front-end processing, and so I will only briefly touch on that. So to give you sort of a picture of where I'm going to go, I'll start with a very brief history of speech recognition, especially focusing on events that led up to sort of a general consensus that the right way to go about speech recognition is to use a probabilistic framework. I'll then go through the various parts of a speech recognition system, the feature extraction, acoustic modeling, which is really the heart of this talk, language modeling, search, and then, if there's time, a little bit of sort of philosophy and perspective, talking about what the current state of the art is in speech recognition, what the strengths are, and where we really could stand to improve the technology. On the language modeling, I'm also assuming that you've all seen n-gram language models, again, in Jason Eisner's talk. So, a brief history of speech recognition. If you look in history, it all began with a toy in the 1920s called Radio Rex, which was based on analog circuitry, and it was a speaker-independent one-word recognizer. If you said Rex to it in just the right way, a little dog, which doesn't show up too well in this picture, would pop out of its house. Yeah, so actually a lot of speech technology has shown up in toys. Some of the first really viable synthesis was the TI Speak and Spell. Okay, so going on to what we call the early years, which is sort of the 1920s through the end of the 1960s. There was active research on speech recognition. However, it was limited very much by what sort of processing researchers could do. For the bulk of this time, they were pretty much stuck with analog processing, what you could do in continuous time with analog circuits. Because recall that digital signal processing didn't really start as a field until the 60s. So generally, these tasks would focus on fairly small vocabularies, a small number of speakers who were highly cooperative, and would employ fairly simple signal processing approaches looking for energy in certain frequency bands, dominant frequencies and such. But if you look at the literature, you do see some ideas that are actually pretty central to speech recognition now. Things like statistical training, language models, but there was no good way to put it all together. So by the end of the 60s, you had people using digital signal processing on the best computers available at the time to try to do speech recognition. A lot of the approaches tended to take a more classical AI perspective, where they tried to do rule-based reasoning, blackboard systems, combinations of experts, things like that. And it led to actually to a fairly cutting letter to the editor in the Journal of the Acoustical Society of America called With or Speech Recognition from John Pierce of Bell Labs. Some of the choicer comments, some of which appeared in the abstract. Speech recognition has glamour. Funds have been available, but results have been less glamorous. Speech recognition has a scarcity of people in the field, of people who behave like scientists and of results that look like science. And my favorite, it would seem appropriate for people to ask themselves why they're working in the field and what they can expect to accomplish. Now, this had a really bad effect, which was that it killed speech recognition research at Bell Labs for many, many years, at a time when Bell Labs was really the premier institution doing work on acoustics, speech, and signal processing. It did have a salutary effect, though, because it did provide partial impetus for the first project in which the Defense Advanced Research Projects Agency, or DARPA, would fund speech recognition research. The D up there is in parentheses because depending on administration, the defense in DARPA gets added or dropped. So the program goal here was to achieve a breakthrough in speech recognition by integrating speech knowledge, linguistics, and AI. And one of the key ideas that was introduced by this DARPA program was the concept of competitive evaluation. The 4 groups that were funded, 3 or 4 groups that were funded through this program were required during the program to test the recognition systems on a common task. This common task included connected speech, so people weren't putting spaces between the words. You would have what was, for the time, a large number of speakers, although cooperative ones. They were trying to do a task. It was a fairly large vocabulary, 1,000 words, with an artificial syntax, so there was some control to the task. And what they were going for was something they called semantic error rate, and they wanted less than 10%. I'm not actually sure the details of that measure. And they were going for a few times real time on a 100 MIPS computer. So what that means is if you had a 10-second chunk of speech that you were processing, you wanted to take 30 to 40 seconds of processing time on what was by far the fastest sort of computer available at that time, if not actually faster than what was available. But this was sort of to try to push the technology. So what happened in the first evaluation? Well, there were 4 systems tested. 3 of them were classical rule-based systems, classic AI. I tried to use knowledge. Then there was this system from Carnegie Mellon called HARPy that integrated all of the knowledge sources together into a finite state network and then trained the entire system in a unified way. And HARPy won hands down, just wiped the floor with the other systems. So that led to the popularization of a statistical approach to speech recognition, where we cast the task as in a probabilistic framework. We try to find, let's see, here's the laser pointer. What I'm going to denote here, W hat, the best possible word sequence, which is defined initially as the most probable sequence of words given your acoustic input and a set of parameters. Now, that's really hard to compute. So what we do is we apply Bayes' rule here to break it down into the probability of the acoustic features, sequence of them given the sequence of words, a prior probability on word sequences, and then a prior probability on the acoustic features. We can pretty much drop the prior on the acoustic features because those are given to us. And this ends up being what we often call the fundamental equation of speech recognition. Now, the way this is implemented in the speech recognition system, which I'm going to talk about as having 4 main components: a feature extraction block that converts audio into a sequence of acoustic features, an acoustic model, a language model, and a search process that searches through a very large, complex search space to come up with the best sequence of words. Now, we can map these blocks onto this fundamental equation as follows. The feature extraction block simply computes the features given the audio. The acoustic model computes this probability here, the probability of your acoustic feature sequence given a sequence of words and parameters. The language model provides the prior on the word sequences, and then the search block is responsible for doing this argmax operation. So moving on to feature extraction, which you've spent much of the morning hearing about, I'm going to give a very high-level overview. So what are we trying to accomplish in the feature extraction phase? We want to characterize the signal aspects that we're getting that have something to do with what's being said. We want to suppress signal aspects that are irrelevant to the linguistic message. In many languages, that can include pitch, but not things like Chinese or other tonal languages. You don't really care too much about the characteristics of the speaker. Is it a child? Is it an adult? Is it somebody who's quite elderly? You'd like to suppress things like accent, acoustic effects, background noise, and so on. You want a concise representation. The methods that we use for acoustic modeling tend to do better if they don't have to deal with very high dimensional features. And finally, you want the features that you produce to conform to the constraints of the acoustic model. To be more specific, the acoustic models that we use rely on Gaussian mixture models, and we tend to make an assumption that the covariances of these Gaussians are diagonal. And so you want the features to have that kind of that kind of structure. You want there to be no correlation between the features if you can condition on the acoustic class that you're looking for. Okay. So we use a small handful of methods to meet these goals, and Hynek discussed them in more detail before me. So first, we want to extract some sort of a smoothed spectral envelope. We'll use techniques like the fast Fourier transform or linear prediction or some combination of those. We want to warp the spectral envelope such that we have a very high resolution at low frequencies and a lower resolution at high frequencies. This can be justified in a couple of ways. First, it reflects more or less what mammalian auditory systems do. They have higher resolution in the low frequencies, lower resolution in the high frequencies. Also, if you try to quantify the distribution of information across frequency in the speech signal using techniques like mutual information, you're going to find that you have more information in the lower frequencies. So doing this sort of a warping of the frequency scale tends to equalize the contribution of the different dimensions of your representation. You want to compress the envelope that you've computed to limit its dynamic range because you have a very wide dynamic range. You want to do some sort of a decorrelation of the spectral representation. This is trying to match the constraints of the acoustic model, which likes diagonal covariances. And you also want to include some information about the local temporal evolution of this spectral envelope. One way to do it is to do a simple first and second order differences and then append those to your feature vector, or you can concatenate, say, 9 successive features into a large supervector, project it down to a lower dimensional space and use that. Now I'm sure Hynek discussed other perspectives on this where you want to look at the evolution over longer periods of time in narrow spectral slices. I'm talking only from the perspective of doing spectral envelopes because that's really sort of the dominant approach right now. That's changing thanks to Hynek and his colleagues, however. Okay. That's all I'm going to say about feature extraction. So moving on to the acoustic modeling, where we're trying to come up with a probability of the sequence of acoustic features given a word sequence. Most large vocabulary systems are going to model words as sequences of phones. A phone is considered to be an atomic unit in linguistics. The idea is that you can't break it down into smaller units in time, and if you change the identity of one of these sounds, you can change the word. So think of it as basic sounds like a, t, b, and so on. Now there is a perspective that phones can be decomposed into articulatory features that have to do with the positions of your lips, your tongue, and so on. Again, that's an area of research. It's not really the dominant approach right now. One of the advantages of this representation is that you can learn how to represent words that you never saw in your training set. So what you're learning about are these basic phone units or phonetic units. You can concatenate them together to form models of words that you never saw when you were processing your training data. It also gives you a form of sharing. So here I'm showing in this sample lexicon where I've got words on the left and sequences of phones on the right, 2 pronunciations of the word the here, and this one, which is the. And instances of each pronunciation of the will potentially contribute to a model for the sound the. So these are some of the advantages of this approach. We're going to model the phones with hidden Markov models, which you saw, I believe, last week in the context of a discrete alphabet. So a very, very typical phone model will have a set of 3 states connected left to right with self loops to model the potentially different temporal evolution that you get with different productions of the phones. You'll have a beginning, a middle, and an end state. And one thing to note here is that we've got a generative model of speech. We're assuming that there's this process that we can't see, and each time you have a transition in a state, either the state to itself or the state to the next state, it's going to produce some observation. Last week you were looking at observations that were coming from a discrete alphabet. Here, these observations correspond to the acoustic features that we're taking, and so we're working in a continuous space. Now, there's 3 key operations that we need to know about in doing speech recognition with these hidden Markov models. First is the forward-backward algorithm, which you saw last week. From the perspective of speech recognition, it's a tool for giving us a probability distribution over the hidden states Q at each time t, given some sequence of words and a sequence of acoustic observations. It's useful for training our models, and I'll go into more detail on that later. A second operation is what I'm going to call the constrained Viterbi algorithm, or forced alignment, where you're given a word sequence and an acoustic observation sequence, and your job is to find the best sequence of hidden states. It's going to have the sequence of hidden states is going to have the same length as the acoustic observation sequence. The third operation is the Viterbi algorithm, which finds the best state sequence given just the acoustic observation sequence. Here, though, we're going to have the constraints of the language model, so it actually is going to look a lot like the constrained Viterbi algorithm, only it's a lot less constrained. You can produce any sequence of words that can be produced by your language model. And this is usually the algorithm that's used for doing the recognition process. The other thing you should know is that phones really aren't a good enough basic unit for doing speech recognition. So I've got an exercise here. As you put your hand in front of your mouth, you say spin, and then you say pin. Yeah. Now, do you notice a difference when you do this? In pin, you get a fairly large puff of air coming out. When you say spin, it's much smaller. So the linguists would say that the p or p in pin is aspirated, and the p in spin is unaspirated. If you look at a spectrogram of the two p's, you're going to see that they actually look kind of different. And you see this sort of effect throughout speech. Enoch touched on this in his talk. Co-articulation effects. The identity of the phones around the phone that you're trying to recognize will actually change its acoustic realization. So you have to have some way of modeling that. The linguistic term for these, by the way, for these phone variants is allophones. So how are we going to model allophones? What we're going to do is we're going to use a simple data-driven method based on decision trees. So the first step is that we're going to take all of our training data. We're going to assume that we have some speech recognition system that we've already trained up that is sufficiently well matched to the training data that we can use it to do forced alignment. If you don't have that, well, I'll talk about how we deal with that case later. Then, for every state in your HMMs, for example, here I'm going to assume that we have, in this example, for example, you have the beginning state, the middle state, the end state, all the way through, for English, the end state. You want for each state to collect all the observations that are assigned to that state by the forced alignment process. And then you want to grow a decision tree by taking all of the data and doing a recursive splitting using binary questions to form a tree. Generally, you stop this tree growing process when the number of samples at any node in your tree falls below some given threshold. That's a design parameter. I'm going to show you an example in the next foil to give you a picture of what this looks like. The questions are going to be about the identity of nearby phones. So if you're at working with a certain phone, say you're going to look 1 or 2 positions into the past, 1 or 2 positions into the future, and you're going to ask questions like, is the second phone before me a buh, or does it belong to some class, say fricatives, and so on. The criterion that we're going to use for choosing the best split is data likelihood. So we're going to model the data in a node with a single multivariate Gaussian distribution with a diagonal covariance. And we're going to say, okay, if we model all the data in this node as a single Gaussian, we get some likelihood out. And then we're going to look at all possible splits of the data in that node. We're going to train models for each possible split, measure the likelihood, and choose the question that gives us the best improvement in likelihood. The advantage of doing this is that it's really computationally efficient. All we need to do is do sums of the feature values and sums of the squared feature values, and we can get these likelihoods quite efficiently. Then, once we have a set of trees for each of these phone models, we're going to do a pruning, again using likelihood to reach some fixed number of states. So we're going to do the pruning globally across this entire forest of trees, getting rid of the splits that give us the least improvement in likelihood, again, looking over all of the trees until we get some number of states. So to give you an example, large vocabulary systems that may be trained on hundreds or thousands of hours can use anywhere from 4,000 or 5,000 states to 20,000 states, depending on the language and the task. That's also a design parameter, something that we have to choose. So when we get a new data set, we try a different number of states for the data set, and we look at the performance of the recognition systems that we get out, and we choose one that gives us the best error rate. So it's a fairly labor-intensive process. Okay, so this is a sample decision tree taken from a speech recognition system that I built, and I'm working on the English phone ah, the beginning state. So the first question is the phone what this means here is up here on the left you have a number, and that's an index to phonetic position. So this is saying I'm going to look at the phone that came just before me, and I'm going to say, is it sonorant? Sonorant basically means pretty much includes all of the vowels and a lot of the voiced but continuous phones. Then if the answer is no, then okay, is the phone 2 positions in the past silence, and so on. So some sample questions here. Nasal is a phone in the set N, M, and G. Labial, retroflex, fricative. This is an example taken from English. This is actually one place where you do have an opportunity to bring knowledge about linguistics into a speech recognition system, because you want to ask questions that pertain to the production of the speech, positions of the articulators, and also possibly to properties of the language. So you may have to ask questions in Chinese, for example, about the tone associated, the trajectory, the pitch that's associated with the phones around you, and so on. So we can also ask questions about individual phones. So you'll say, is the phone to my immediate left an F? Typically, you'll have between 60 and a couple of hundred questions in your question set. Okay. Once we have these context-dependent states that we've defined through the decision trees, we're going to model the distribution of acoustic features associated with each state using a mixture of Gaussians. So we're working with multidimensional features, typically somewhere on the order of 40 dimensions. And we're going to use for each state a collection of Gaussians. So if you ignore the W up here, this is a single multivariate Gaussian distribution. The W is the weight of the jth component in the mixture, where you have some k components. The weights are constrained to sum to 1. The mu's denote the means of these Gaussians, and the capital sigmas denote the covariances. And generally, we're going to constrain these Gaussian models so that these covariances are diagonal. In the past, the justification for this was that we didn't have a lot of training data. We simply couldn't train up all of the parameters in a full covariance model. So if you have n dimensions, you're going to have n times n minus 1 over 2 parameters in your full covariances. Nowadays, when we're training on hundreds or thousands of hours of speech, that's a less convincing argument, but the new argument is that you have a lot more expressive power if you have n minus 1 over 2 diagonal covariance mixture components than you do a single full covariance Gaussian. Though in some cases you will see full covariances used. So why do we use Gaussian mixture models for acoustic modeling? One is that they're mathematically tractable. It's really easy to work with this. These end up looking, if you take the log of these likelihoods and ignore the mixtures, you end up with things that look like weighted Euclidean distances. It's easy to do the math. It's easy to collect statistics, train these things. Also, if you have enough mixture components and you have enough data, you can approximate a very wide variety of data distributions. So it's sufficiently flexible that you can model all sorts of possible distributions of data coming in if you have enough data and enough mixture components. Okay. Now, how do we train these? We use the expectation maximization, or EM algorithm. So if we assume that we have some initial set of parameters, what we can do is we can come up with a probability, if we're looking at a single mixture of Gaussians. We're going to say that the probability that the jth component in that mixture produced an acoustic feature vector x, given that we're in a single state, is going to be the likelihood that's assigned by that single mixture divided by the sum of these likelihoods over all of the mixtures all of the components in the mixture. So if you go back here, this is the sum over all of them, and then we're just going to take the jth likelihood and normalize to get something that looks like a posterior probability. So these values are constrained to be between 0 and 1, and if you look over all of the components in the mixture, they sum to 1. And this is your expectation step. Then we're going to treat these as weights in our Gaussian update. So for updating the jth component of the ith state, we're going to weight the feature vector by its posterior probability in the mixture. We're going to sum that up over all of the feature vectors we have, and then we're going to normalize, and the normalization factor here is just the sum of all of these posterior probabilities over all of the data. So it looks like a standard Gaussian update, except that we have these weights that are applied to each feature vector. Similarly, we do the same for the covariances, and this is called the maximization step. We just then iterate this process until we get some sort of convergence. This is maximum likelihood training for Gaussian mixture models. Now, there's some practical issues that have to be addressed in here. First, how do you get your initial estimates of your, how do you get your initial parameters of your mixture components? There's two choices. One looks a little bit like the k-means algorithm. You just take your data, you randomly assign samples to individual components. You do your parameter updates, and that's your initial set of parameters. Or you can do mixture splitting. What that means is you take all of the data that's assigned to a Gaussian, to a single state. You train up a single Gaussian. That's easy. You just do it in one pass over the data. Then you take that Gaussian and you say, okay, in what dimension do I have the largest variance? In that dimension, I'm going to then produce two Gaussians that have almost the same parameters. They're going to have the same covariance matrix, and the means will be just offset very slightly from one another in that dimension that has the largest variance. Then I'm going to run the EM algorithm until I get some sort of convergence. Then I'm going to continue to split the components, do EM updates until I have the desired number of components. Both methods work, and you'll see them in different contexts. There's also an issue of regularization. So can anybody tell me what happens if one of these mixture components gets assigned only a single data point? Okay, what happens is the mean of the Gaussian becomes the same as that single data point. Your variance goes to 0. And if we go back up here and consider just a single one of these, if the variance in any dimension goes to 0, well, that's 1 over 0. You end up with basically an infinite likelihood, mostly actually due to this term here. So you can actually get solutions, maximum likelihood solutions, that give you an unbounded likelihood, but they're only modeling a single point. These aren't useful to us. So we're going to do a form of regularization where we're going to say, okay, the values of the variances that we're learning can't fall below a certain value. And if there's a mixture component that doesn't get a lot of data assigned to it, we're going to throw that out. We're going to take some other component of the mixture, split it, and continue training. There are fancier versions of regularization based on Bayesian models where we put in priors, we do a lot of math, we come up with a very nice principled method. To do it, we might need to use variational methods to do the training. You can write a lot of papers that way, but if you're interested in doing speech recognition, just well-implemented heuristics have the same effect and are a lot cheaper to implement, a lot easier to think about. The third problem that we have to worry about that's a practical issue for these Gaussian mixtures is model selection. So how do you decide when you have a data set how many Gaussians you're going to use in each mixture component? There's several standard approaches to doing this. One of the most common is just to say, okay, every state is going to have 4, 8, or 16 mixture components. That's going to be a design parameter. We'll try several settings and pick the one that gives us the best performance. Another fairly popular approach, or actually this is a standard one for us at IBM, is we're going to say, okay, we have an initial forced alignment of the data. We're going to look at how many frames get assigned to a single state, and then we're going to say, okay, we'll assign a number of components that's proportional to the number of frames that got assigned to that state to the power 0.2. It's a heuristic. And then we have to choose the proportionality constant, and that's, again, a design parameter. Do you want 50,000 Gaussians in your system? Do you want 10? Do you want 200,000 or more? It depends on how much data you have. It depends on other constraints, like how fast you want the recognizer to go when you're doing recognition, and you're also going to look at system performance and say, you know, what's the best error rate that I can get? And then finally, there are a set of Bayesian methods, either involving putting priors or doing approximations such as the Bayesian information criterion, which penalizes the likelihood with a term that's proportional, I think, to the log of the number of parameters multiplied by the number of data points, if I remember correctly. Okay, so how do we put it all together? Again, assuming that we have some initial set of parameters for our models, we can use the forward, backward, or Viterbi algorithm to get an assignment of each feature vector in our training data to an HMM state or states. If we do the Viterbi algorithm, it's going to be a hard assignment. So each feature vector in the training data is going to be assigned to a single state. If we use forward, backward, it's going to be a soft assignment. You're going to get a probability distribution over HMM states, and it's going and you can then treat these posterior probabilities as an additional set of weights that are used in your Gaussian mixture updates. Then, given this assignment, you run the EM algorithm to get a set of new Gaussian mixture model parameters, and optionally you can update the transition probabilities between the HMM states. In large vocabulary recognition, we typically ignore transition probabilities because they're completely swamped by the likelihoods coming from our Gaussian mixture models. And we're going to just rely on the language model to provide effectively transition probabilities between words. Then for the training, we just iterate this process until it converges, or until we're tired of using the computers. Okay, so where do the initial model parameters come from? The easy answer is if you already have a speech recognition system that you can use to do forced alignment because it's well enough matched to your training data, you can just shovel all of your training data into the speech recognition system, run forced alignment, get a Viterbi assignment of all of your feature vectors to your states, then using this alignment, train your Gaussian mixture models. Do the random assignment to your components of your Gaussian mixture models, run EM to get your initial GMMs, and then you can iterate the process. Now that you've got Gaussian mixtures that are specialized to the current set of training data, you can just go back to the previous overhead here and just iterate steps 1 and 2 until you're happy. Okay, what if you don't have any speech recognition system for this data? What if it's a language that you've never dealt with before, something like Hausa or Ewe or something you've never heard of? But you have word level transcripts. The standard method then is to use something called flat start training. What you do here is you have, for each utterance, you have a word sequence. Presume you've either paid a linguist or some expert to give you a set of pronunciations for each word in your training set so that you can map a sequence of words to a sequence of phones. What you're going to do is you're going to say, okay, if I have multiple pronunciations in my lexicon, I have no idea which pronunciation is being used in any one of these sample utterances. So I'm going to, for each utterance, if I have multiple pronunciations per word, I'll just pick one randomly. I'm also going to ignore the fact that there is possibly silence between these words. So I'm going to just do a very simple-minded mapping of this word sequence to a sequence of phone states. I'll probably assume that I've got silence at the beginning and end of each utterance because that's usually what happens in recordings, and it gives me a way to get initial model of silences. Then I'm going to say, okay, I have n frames of speech in an utterance, and I have some number of phones. I'm just going to uniformly segment my acoustic features, that feature sequence, based on the number of phones I have. So if I have m phones, I'm going to get m segments. I'm going to assign those to, I'm going to assign in order each segment to the phone in this, phone sequence that I've produced by doing this very simple-minded mapping. And then I'm going to model these states, which are not going to be context dependent now, using just a single Gaussian component. Then I'm going to run the forward-backward algorithm a lot of times, 40, 80, something like that. That's going to give me an initial set of models that are very, very coarse, very, very crude, but it's a place to start. This method is surprisingly effective. The performance of these systems that are trained with flat start only are quite poor, but it's enough to let you bootstrap. It's enough to then turn around and say, okay, now I've got an initial set of models. Now I can go back and I can align my data, and I can let the models choose the pronunciations. I can let the models decide if there's silence between words or not. And then I can just iterate the model building process, building successively more complicated models on my data until I'm done, until I'm happy. So one very common technique that you're going to see in speech recognition is iterative training, where given a data set, you'll start with a very simple model set. You'll train up those models. Then you'll use that as a way to get another set of alignments. And then you'll train up more detailed models, and you may iterate 3 or 4 times, particularly if you're starting from a flat start. Okay, moving on to language modeling. Why do we need a language model? Well, the mathematician's answer is that we've used Bayes' rule. We have to have a prior distribution over word strings. An engineer's answer is that it makes the search process easier. You can use the language model to rule out very unlikely sequences of words, and you can make the job of the acoustic model much easier. The user is going to say, well, it's a dictation system, for example, and it's going to, help me actually get sentences like this, which is taken from an old IBM Via Voice ad, right. Write a letter to Mrs. Wright right now. Well, you've got, homophones all over the place. How do you know which version to put in? You have to look at the words that came before you and make a decision. Okay. Now, the difficulty in modeling word sequences is that the space that you're putting a probability distribution over is huge. So if you want to do an exact computation of the probability of word sequence W of length M, you can break it down this way. You can say, okay, well, we've got a start state that we're going to see. Probability of seeing that is 1 because we're processing something. Then, given that we've seen a start state, we can have a probability distribution over words, and we can get a probability of the first word. Then we look at the second word, we can come up with a probability of the second word, given that we had the previous 2 before, and so on. And here, there's a mistake. No, it isn't. Okay, so the S here and /S are special symbols to mark the start and end of sentence. The problem is, as you get conditioning on longer and longer sequences of words, the probability of actually seeing any given sequence drops exponentially with them. So you have a big data sparsity problem. You're not going to observe most of the sequences that you might like to. What are you going to do? You're going to say, okay, ignorance is bliss, and we'll just ignore the stuff that's really far back in history, and we'll just say, model our probability distributions, conditioning, say, on only the previous 2 words, for example. So we go from an exact computation that has a serious problem with sparsity to an approximation that has a less serious problem with sparsity. But there's still issues that I'll address in the next foil. This example here, where we're looking at the probability of word given the previous two words, is called the trigram language model because we're considering groups of 3 words. Okay. How do you go about training a language model? First thing you do is you collect as much text as you can possibly get your hands on, preferably as closely related to the task that you're going to do as possible. But any text is better than no text. And then you're going to count up word co-occurrences to the maximum desired order. So in the trigram example, you're going to count up count up every time you see a word given the 2 words that preceded it. The next thing you're going to do is you can then train up a language model. You can get probability estimates now by just doing maximum likelihood. You've got counts for each word given the preceding 2 words. You can normalize, you can get probabilities. That's not going to work because even with low order n-grams, there's going to be some n-grams that you might see when you're doing recognition that you never saw in your training data. The maximum likelihood estimate is going to assign a probability of 0 to that event, and your recognizer's not going to be able to hypothesize or output events that have 0 probability. So you actually have to take some of the probability mass that is assigned to events in the maximum likelihood estimate, and you're going to have to move that onto events that were given 0 probability because you never saw them in the training data. There's a very large literature on doing smoothing, and at the end of this presentation, which I believe is going to go up on the website, there's a link to the Columbia course, and there's actually a very nice discussion of smoothing there, written by Stan Chen, who's at IBM and is something of an expert on the topic. Another thing to note is that if you're doing language modeling, you're often going to get better results if you have text from multiple sources. You're going to get better results by not lumping all of that together, but by training up independent language models on each source and then doing an interpolation. And you can take held out data that's representative of the task that you're trying to do and then optimize performance on that held out data to get the best interpolation weights. To give you an example, suppose you're doing recognition of telephone conversations. You're going to have some set of transcribed telephone conversations that you can use for your training your language model, but that's typically going to be kind of small. On the other hand, there's tons of data that you can get by, say, going out on the web and collecting transcripts from CNN or from newswires and so on. You can also go and train a language model on that data. But there's a mismatch because people talking to each other don't sound like broadcasters reading the news. So it's not going to be quite as well suited to the task of recognizing telephone conversations as the original data, but it's going to give you a better coverage of the general properties of English. So you could say train up your CNN model, you can train up your conversations model, and then you can interpolate them by weighting the probability estimates that come out of the 2 models, and you can optimize that interpolation weight. It's a very powerful technique that works quite well. Yeah?
Sorry, are you taking questions?
I'm happy to take questions at any time. I'm used to being interrupted.
So I have a beginner's question.
Yeah.
Do you model stuff like those kind of breaks in speech in your language model, and you actually want to produce that because that's part of your recognized speech output?
That's an excellent question. You do need to model them, especially if you're doing conversational speech, because often uhs and ums precede things like repairs, where the person said something they didn't mean to say, and then they're correcting themselves and they'll go, and then they'll go on and they'll repair. So there's actually some structure there that you want to model. And you do want to be able to actually model those in the language model. Often in the DARPA-funded tasks, though, those are treated specially if you're doing scoring. You're going to say, okay, if you get it right, you get credit, but if you delete the uhs and the ums, we're not going to penalize you. Another detail on the language modeling is how do you handle silence? There, what you usually do is you're going to say, okay, I'm going to not model the silence in the language model explicitly. It's just not going to appear as a token. And the main reason for doing that is we rely so heavily on text sources for doing language modeling, and how do you insert silences into newspaper text? You can't do it. So what you do is you strip any silences out of any conversational material that you have. You train up the language models without it, and then you're going to say, okay, silence is a special token. It's going to be a token that can appear anywhere. It's not going to change your history, though. So the jargon for that is that it's transparent in the language model. What that means is that these histories here, where you're saying the probability of some word is conditioned on the preceding two words, if silence appears somewhere in the sequence, you actually delete it for the purposes of doing this computation. And you're just going to assign some prior probability to silence. And that's another design parameter that you tweak to get the best performance out of your recognition system. That was a good question. Any others? We'll go to stopped. Okay, moving on then. Okay, yeah, covered that. So a little bit of practice over theory here. This fundamental equation of speech recognition that I put up is actually a lie, because we don't treat the acoustic model and the language model the same. We actually, in doing the computation, this argmax, we give a heavier weight to the language model. It's denoted here as an exponent on a probability. In practice, of course, because we're looking at products of probabilities, what we really want to do is we look at sums of log probabilities. So it becomes a linear scaling of log probabilities coming out of the language model. And this alpha here, this weight, is going to be somewhere between 5 and 25. It's going to be set to optimize performance on development data. I've heard a lot of arguments for why we do this, none of which is particularly satisfying. In practice, what you see is that the dynamic range of the probabilities coming out of your acoustic model is much larger than the dynamic range of these. You could say that maybe the acoustic model is overconfident. That's actually the explanation that I've heard that I like the best. But in practice, this is done, it works, and we just ignore the fact that we're no longer really doing a probabilistic model. Okay, moving on to search. So speech recognition is, the search process is the same as searching for the lowest cost path in a very large, complicated graph. This can be done as Viterbi search, where you're trying to find the best sequence of states in the search graph. The nodes in the graph are going to correspond to entries in a large dynamic programming chart, and the arcs in the graph are going to correspond to HMM states, in which case you're modeling acoustic observations, and we'll have costs coming from the acoustic model, or they can also correspond to words, in which case there are costs which are proportional to the negative log likelihoods that are coming from the language model. So this is actually looking a lot like what the Harpy system did over 30 years ago. We're going to think of our search space as a very large finite state network. We've done statistical training to optimize parameters for this network, and we're just going to integrate all of our knowledge into here and then do search on it to come up with our best word sequence. So at each time step during recognition, what the dynamic program is going to do is you're going to update the entries in the chart with the lowest cost path that could have reached the corresponding state. When you get to the end, you look over all of the states in the search graph that could correspond to the end of the utterance. You find the best one, and then you search backwards to find the sequence of words that led you there. So I'm saying it's a graph. What does this graph look like? So let's take a very trivial example, which is a language model that can only give you two utterances, the dog or good dog. Now, if you think of that as a graph, now you say, okay, you can put silences in between words. So you need to model a possibility that after the start of the utterance, I might have silence, or I might immediately have the. Or I might have silence, or I might immediately have good. Similarly, I could have silence before dog or not, and I could have some silence at the end of the utterance or not. So already we've gone from something that's a fairly simple finite state network to something that looks a little bit more complicated. Now, what if we have multiple pronunciations of words? Take the, for example. The can be said the, or the can be said the. So in the graph, if you look at two states with an arc going between them that corresponds to a the being produced, you have to turn that into a state that corresponds to the v phone, and then one that corresponds to and one that corresponds to e. And then anything that follows this state then has to be duplicated. It gets more complicated though, because these are just phones, but what we're really modeling are allophones that we found using these decision trees. So take a case where we're only going to model a phone depending on what phone follows it. So we'll have two variants here, the followed by and the followed by e. So this is the DAW. So this is actually a snapshot from the original graph corresponding to going from the to dog. So the, DAW, and we dropped g. Again, we go from something that's fairly simple to something that's, again, more complicated. Now, if we were also looking, say, not just to our immediate following phone, but two phones into the future, if we're looking into the past, then you can, again, have a really large expansion of the graph due to this allophone modeling. End result is that you have a really, really large, complicated search space. If you model one of these, if you look at one of these graphs for a large vocabulary task, you could have, say, 45 million nodes in your search network and 190 million arcs. And that's actually after you've cut down your language model significantly. If you were to use a very large language model, it's even bigger, and it's something that we can't deal with in current computers given memory constraints. So if you imagine that you have 45 million nodes in your dynamic programming chart, and you want to update each one of them at every time step, and you might be dealing with a really long utterance, this becomes extremely expensive computationally. So we cannot do an exact search. We have to do some sort of an approximation. We have to throw out unlikely paths as early as we can. So this process is called pruning, similar to pruning away dead or unpromising branches on a fruit tree. And there are two fairly standard techniques that are used for speech recognition search. The first is called rank pruning. So you look, conceptually, you look over your entire set of states in your search graph, and you're only going to keep the top, say, 5,000, 10,000, 15,000, the ones that are most likely at any given point in the search, and you're only going to consider the evolution of the search from those most likely states. That works because when you start, you only have a single start state or a small handful of start states, and you just apply this rank pruning at each step to limit the size of the search. You can also do what's called beam pruning, which is at any given time in the search, you say, okay, what's the most likely partial path to the graph? What's the score of that? Okay, I'm only going to consider paths that are within some factor, which is a parameter, of this current best score. Anything that scores worse than the best score by that factor, I'm going to just throw out. I'm going to make them inactive. I'm not going to extend those paths. It's called beam pruning. Most modern speech recognition systems use both. They have slightly different properties, and in practice, you get the best performance if you do both. Yeah?
What's the intuition into choosing N?
Again, it's mostly looking at trade-offs between how much time you're willing to spend on computation and how accurate you are. So for the English example here, where you have 45 million nodes and 190 million arcs, if you keep just the top 15,000 states in that graph, which is a very small fraction of 45 million, you don't see any degradation at all over a completely unpruned search. If you want, but you spend more time on computation. So what we typically think of is that there's a trade-off between the accuracy of the recognition and how fast it goes. And that is one of the parameters that plays into that trade-off. So it really is, it's set based on sort of what your goals are for the recognition system. How much time are you willing to spend on computation, and how accurate do you want it to be? So if you're in a competitive evaluation, you make N as large as possible. If you are giving the system to a customer who wants to be, say, indexing CNN, and they want to have the output from 5 minutes ago, if they're only willing to wait 5 minutes so that they're only delayed by 5 minutes from what's going on, then you have a much different decision about how to set it, and you want to cut it down quite a bit. And that applies to the beam pruning as well. If you set the beam width really wide, you're going to spend more time computing, you're going to have a more accurate result, and then, but if you need to go faster, then you need to reduce that value so that you throw out more paths. Okay. Now there's two dominant methods for doing the search. The one that's been quite popular lately, thanks to the work of Miramori and others at AT&T, is to do what's called static search. So the idea is that you really do build this large search graph. You can use finite state machine techniques to represent your language model, the set of words that you can recognize, and your decision trees, and you can use these techniques to compile all of these knowledge sources into a single very large search graph. And then you can apply standard finite state machine methods like determinization and minimization to make that search graph smaller, and also to move the weights around in it so that you get better behavior if you do prune your search. Now there's some advantages to this. A static decoder can be very, very fast because all of the hard work of representing the search space has been done offline. You've pre-compiled it, you've written it to disk. You don't need to do any work at the time. You just have to implement the Viterbi search. It can also be very, very simple to write. You can do it in a couple hundred lines of code easily. Disadvantage is that when you do the graph compilation, you're going to need to spend some time because it's an expensive process. Typically, people who are in the business of doing speech recognition using static decoders go out and they buy at least one machine that has as much RAM as they can afford. And they need to often use a smaller language model than you might otherwise use to compile the static search graph. Now, there are techniques that you can do where instead of producing a single output, you produce a graph that represents the most likely hypotheses in your search space, and then go back and apply a larger, more complex language model to this graph called the lattice, and you can get pretty much the same results as if you used the large language model originally. The other option is to use what's called a dynamic decoder. Here you're constructing the relevant portion of your search space on the fly. The nice thing here is that you can use as large of a language model as you want in the search, but you're going to be a little bit slower, and it's going to be a more complicated piece of code because the dynamic decoder has to do all the bookkeeping to say what parts of the search space need to be expanded, needs to maintain those, so you're allocating and deallocating memory and so on. So it's a lot harder to get right, but they're both useful tools in practice. Okay, where do we stand? Yeah, I've got time. Okay, I haven't said it yet, but if we're talking about speech recognition performance, so in the original DARPA evaluation back in the 70s that Harpy won, they had this concept of semantic error rate. What we look at nowadays most of the time is word error rate. So what we do is we say, okay, we have a reference that we got from having one or more highly trained people listen to all of the speech, write down what was said. Example, the dog ate my homework. And we're going to take the output of the speech recognition system, and we're going to align these two hypotheses. What that means is we're going to do dynamic programming to try to line up the words such that as many of these words as possible match. Then we're going to go through this alignment, and we're going to say, okay, well, if the reference says there's one word, but we saw a different word, well, that's a substitution error because we substituted one word for another. If there is a word in the hypothesis that corresponds to no word in the reference, well, we inserted something. That's an insertion error. If there's a word in the reference that's not in the output, well, that's a deletion error. And we're going to sum up all of these errors. I'm going to divide by the total number of words in all of the references and multiply by 100 to get a % word error rate. Now, one of the interesting things about this is that if you have really catastrophically bad performance from your speech recognition system, word error rate can be above 100%. Not a desirable state of affairs, but sometimes it happens when you're first starting on a task. Or if you've screwed something up, which happens quite a bit. Okay, how do we stand compared to human performance? So there was this paper about 10 years ago now, 11 years, by Rich Lippman, called Speech Recognition by Humans and Machines, where he went to the literature and he said, okay, we'll look at some standard tasks, connected digits, the TI digits corpus, Wall Street Journal, which is people reading Wall Street Journal articles out loud, Wall Street Journal with some added background noise, and then telephone conversations. How well do people do if they listen to them and write transcripts, and how well do speech recognition systems do? Some of the speech recognition system numbers I've updated based on more current literature. Human performance hasn't changed. And although I don't know if you did it now with too many people listening to their iPods turned up, maybe human performance would degrade a little. But if you look here, you see that even on very constrained, well, on the most constrained task, people are a lot better than the machines are. If you add noise, people are a lot better than machines are. Telephone conversations, there are huge factors here in performance difference. So what makes speech recognition hard? The main thing is variability. People come in all shapes and sizes. They have all sorts of accents. They have many different manners of speaking. So if you look at speech coming from an anchor who's reading the news, that's usually very easy for both humans and machines to recognize. If you, on the other hand, record a conversation between, say, a student at school and their family back home, that's actually a lot harder for both machines and people to recognize because people tend to talk faster, they make a lot of mistakes, they leave out a lot of information, there's a lot of laughter, talking over one another, and so on. So if we just look kind of over a set of factors, what can make a task hard? Vocabulary size, the larger the number of words you have to deal with, the harder it's going to be, and the more chance that you're going to have words that are confusable. Language model constraints. If you know you're recognizing social security numbers, or if you know that you're recognizing tracking numbers, say for UPS, you know how many digits or alphanumeric or alphabetic characters you have to get. Often things like tracking numbers have some checksums built into them, and you can actually constrain your output to respect those checksums. On the other hand, if you're recognizing broadcast news or conversations, that's much less constrained. Word confusability is hard. There's this classic example, it's hard to recognize speech. Audio quality. If you have variable bandwidth, speech recognition systems cope very badly with that. So an example that I can speak to, we have at IBM a number of systems that we sell to customers that do transcription of news broadcasts. A potential customer came to us with a broadcast in English that was sent over shortwave radio. Now, I'm responsible for the English broadcast transcription system. It does quite well on news broadcasts, which have a bandwidth, which are sampled at 16 kilohertz, have a bandwidth up to 8 kilohertz. They also do pretty well on telephone conversations, which, although they get put in at a 16 kilohertz sampling rate, really only have information up to roughly 4 kilohertz because of the telephone channel. Everything above that gets thrown away. The reason for that is that you have call-in shows, you have enough data in your training set that your models have seen it, you're going to get those pretty well. Shortwave radio has a cutoff that's below 4 kilohertz. And when we took the shortwave data and put it into our speech recognition system, it was terrible. We got nothing out. And it was just that it had just fallen below the amount of bandwidth that we needed that our models had seen, and it broke completely. Background noise, you also see this. If you have a system that's trained only on clean speech that's collected in a studio environment, you add in a little bit of noise, things fall apart. Reverberation is a terrific way to break a speech recognition system. I can hear some reverberation in here. If you had a microphone out there and we're collecting my speech and put it into a transcription system, it would do really badly because there's this temporal smearing effect that breaks the recognition system. Also the frequency response of the channel. If you have different transfer characteristics, if you don't do something to plan for that, your speech recognition system can break. Also speaker characteristics. Fast speech is hard to recognize. Speech from children or speech from the very elderly is hard. Accented speech is hard, especially if you haven't been able to train on it. Vocal tract length is another thing that we have to worry about. So you have different acoustic characteristics depending on the size of the person. You have to model that. If you don't, your performance drops. In general, the rule of thumb is anytime that you get data coming into a speech recognition system that isn't like what you trained on, watch out. You're going to make a lot more errors. So what are the strengths of the statistical approach? Mostly, it gives us a nice, solid mathematical framework for algorithmic development. We can derive things. We can derive different training procedures based on EM or gradient descent. And it lets us compensate for a limited understanding of how speech recognition really works in humans by taking very generic models, a lot of data, and just doing training using a lot of computation. Koenig actually had a very nice summary of this, which is that we use data-driven approaches because no knowledge is better than wrong knowledge. We just let the data tell our models what to do, and we go from there. What are the weaknesses? I already got to this. The Achilles heel of speech recognition is variability. If you get something that you didn't see in your training set, you're not going to do very well on it right now. And that follows directly from using data-driven approaches. Second, it's really, really hard to debug a speech recognition system. If it's making errors, it's very, very difficult to assign blame to say, oh, well, this is a language modeling error, this is an acoustic modeling error, or is it something else? There have been entire dissertations written on blame assignment in speech recognition, and it's still really not a task that I would consider to be solved because you've taken all of your knowledge sources, you've kind of integrated them into this large, complicated graph, and then you're doing search on it. So how do you debug that? Finally, developing speech recognition systems for new tasks, new genres, is a really, really expensive process. You have to pay somebody to go out and collect 50, 100, 200 hours of speech minimally. You have to pay somebody else to go through and do very careful verbatim transcripts. You really do want to get every and in there. You want to get every partial word. If it's a language that you don't have a lot of speakers for, then you have to find people who can speak it, train them to do this very careful verbatim transcription. It's an expensive process. Then you have to pay speech recognition researchers like myself to go and do the model building, tweak all the knobs to get the best possible performance and so on. So that's one of the other weaknesses of this statistical approach is data collection is expensive, data transcription is expensive, model building is expensive. So we have to figure out ways to do better on that. So for more information, like I said, I think these slides will be up on the summer school website, and in the PDF, this is a live link. You can click on this and get to an outline of a full semester class with lectures on speech recognition if you want more details on any of this. And I'd like to acknowledge Stan Chen, who did a lot of the work on these lectures, for letting me adapt some of the material from his lectures for this talk. So I can take some more questions now. Yeah.
So I'm kind of curious about the integration of a language model. And so, like, I imagine if you're transcribing like CNN, right, the language model seems pretty accurate. You kind of know what they're going to say.
Mm-hmm.
But in a conversation, I call my mom and I talk about my cousin. What am I going to say? I feel like that's harder to do.
It depends. In my experience, a lot of the conversational speech is actually easier because in regular conversations, people don't use as many words. But you're right also that there's maybe you have a smaller set of words, but maybe you have less predictability in terms of the sequence properties. The other challenge on CNN is if you have breaking news from part of the world that you've never heard of before, it wasn't in your training data, you have out of vocabulary of words, which is a problem I never talked about. But most speech recognition systems, if they get an input that has a word they've never seen before, they're going to come up with some approximate match by gluing together whatever words they do have in their lexicon, and they're going to completely miss the new words. So that's a big challenge, is trying to keep them current.
In a situation where like a language model is kind of like playing a game with a person who's trying to help. Right?
Mm-hmm.
So what if you find yourself in a game where you're in an opponent who wants to deny you the language model, right?
Mm-hmm.
So they start having a conversation in which they're trying to just, yeah, there's still words they still use, I think, they're not lining up to.
Yeah, if you had uncooperative speakers who know that they're being recorded and they don't want to be transcribed, they can easily work around a language model. Either by using unconventional words that might be out of the vocabulary, or by dropping enough words, speaking sort of telegraphically, such that it doesn't match up well with the constraints that you have. You know, you can drop thes and us and stuff and just say nouns. You could speak Pig Latin. You know, there's all sorts of things that uncooperative speakers could do to really screw things up. Yeah.
So could you talk a bit more about out of vocabulary words then? Like what kind of strategies would you use?
Well, there's a couple strategies. It's been an area of active research. In most large practical systems, you just try to update your language model and vocabulary on a regular basis. If you're doing news transcription, you try to keep on top of it by using web sources, and anytime new words come up, you add them. Or you provide mechanisms for the user to add words to the vocabulary, and you provide some sort of default language model probabilities. Other options are to include in your language model more generic units than words, syllables, chunks of phones, and so on, and let your system hypothesize sequences of those. The trick there is then you have to trade off, because it could potentially hypothesize these generic sequences where it's really getting words that it does know. Another option is to try to go back and do some kind of repair. So Hynek's been involved in research where you look and try to identify segments of the speech that correspond to out-of-vocabulary words by comparing the output from a recognition system that's constrained to only output words and one that outputs sequences of phones. And where there's a significant mismatch, you say, okay, we might have gotten a word that wasn't in the vocabulary. What can we do now? Can we somehow splice in the output from the phonetic system and maybe use some sort of sound to spelling process to come up and hypothesize a word in there? Or can we at least flag it and say, you know, there's something wrong here, there's a word we don't know. But that's actually an area of current research that's quite active.
Are there any real-time systems?
Real-time in what sense? Well, yes. I mean, so you can still go out and buy dictation systems. If you're doing transcription, you can come up with pretty accurate transcripts of speech where the amount of compute time that you use is less than the duration of the signal. Then what you have to do is you say, well, how much latency am I willing to live with? Is it 2 minutes? I'll break things into 2-minute chunks and process, and then 2 minutes later I have the output. So that's real time, but not quite in the sense that you think of sitting and talking to your computer. But you can still buy dictation systems that are used. So the answer is yes. And they can be fairly large vocabulary, and for that we just have to thank the microelectronics industry, Moore's law, and the fact that computers have just gotten much faster over the past 20 years. A lot of the progress in speech recognition has just been driven by having more and more compute available to us for less and less cost. Hynek.
I was wondering about this fudge factor that you call it alpha,
Mm-hmm.
and you said that it's up to 25 times larger, and you said that it's probably because acoustics is overconfident.
Mm-hmm.
And actually, when you were saying that, I thought that maybe the other way to look at it, that's the way I saw it, is that isn't that the acoustics in 25 is worse somehow, that we really don't trust acoustics at all? In order to get a good recognition rate, you have to say, and I trust my language model 25 times more.
That's another way of looking at it, yeah.
Is it? Because that's the way I saw it.
Yeah.
So, like, you know,
25 is an extreme value.
Unit so that we get as good recognition rate as possible.
Mm-hmm.
But if I have to make it 25 times more than the base would tell me, it almost sort of tells me I can't really rely on the data. I have to rely on priors much more in order to get the job done.
Yeah, you can also argue that some of the smoothing that we do in the language models actually makes the language model underconfident. There are word sequences that you probably can safely say really should have 0 probability, because unless you have an adversarial situation where somebody's trying to break you, you just won't have those words in sequence. And the smoothing actually makes those go away too.
You see, I mean, with this sort of, you say the acoustics is overconfident. I think this is really bad, right?
Mm-hmm.
I mean, you know, these overconfident people. I mean,
Right.
Full fountains of misinformation, right?
Mhm.
Tell you something very confidently. I just read about the late Buckley who was willing to discuss the books which he never read.
Mm-hmm.
So really the point of view is that the acoustic, you have hyperactive models and you have assumption of statistical independence. So that you just some.
That's another
You do,
explanation,
and
yeah.
whatever you do at the end of the day, you don't trust your data.
Yeah, yeah. I mean, if you try to do speech recognition with a minimalist language model or no language model and look at what comes out, it's usually horrible. So we really do need to constrain what the acoustic models can
So, of
hypothesize.
course-
So that argues that the acoustic models are broken at
So
some
that
fundamental
happens to
level.
you if you are in a bar or in
Mhm.
a plane or somewhere, you do the language model and you don't rely on the data.
Right.
But it's a terrible situation when you are decoding a very well understood speech, right?
Yeah,
If you think about it.
yeah, yeah.
Maybe we need more recognition without the language model just to see how bad the things are. So we become more humble.
Mm-hmm. Yeah, that's a good point.
It
Yeah.
seems like we could actually somehow test how much humans weight language model versus speech, like translation model or what you call
Well-
acoustic model, using some well-designed experiments.
There's a very smart man named Harvey Fletcher who did some of that many years ago, actually helping to design the telephone system, working for Bell Labs. This was, what, in the 30s or so? Got lots and lots of people to talk to one another over different telephone channels. And what they were doing, the task was that one person would be saying these words in carrier sentences, and the target words that the listener was looking for and trying to transcribe were simple, nonsense, consonant, vowel, consonant, or vowel, consonant, vowel words. And the goal was to correctly transcribe all of these. And he actually looked at what people could do. And the results are really pretty impressive. I don't think there's any way that an automatic system could match what people do in that kind of a task, where there's no prior constraint other than the syllable structure. And you have channel variability, and otherwise you have nothing. People do surprisingly well at that.
And then people that lip read have no acoustic signal.
Right.
Very strong language model.
It's
Yeah.
another constraint, but I'm actually quite interested in this question too, and so far I didn't find any solid answer because people don't seem to be doing these experiments anymore. But I talked to people like phoneticians who deal with the languages they don't know. In the 60s, although that has been now, people would go to Africa and they would record a dialect, or language nobody ever knew. And so I was asking how well they can transcribe such a speech because they don't know the language. That basically all they hear is the sequence of sounds. Answer is about 80–85% correct agreement between two good phoneticians who know the International Phonetic Alphabet, because you have to know how to transcribe sounds which are not in English. But 80–85%, that seems to be coming actually more often. This 80% accuracy in transcribing sounds without level of knowledge of the language is there. In case of Fletcher, it was striking because they were using nonsense syllabi, and it was in very good quality speech. It's 8.5% accurate phonetic recognition. But it was a very unusual situation. People were very well trained, and they were paid to use whatever for the task, and so on and so on. So, but in a normal situation, 80% I think is very realistic.
Mm-hmm. In the 80% case, do people look at spectrographic display? Just listening.
I don't know, but I think listening. That was John O'Hara who was telling me that
Okay.
that was typical number. I guess only listening. Though I don't know, honestly. That's a good question. If they use some.
I feel like to get it right, you have to compare it to people in the native language doing the transcription on the level of people who transcribe.
At the end, but see, there was the experiment question was how well two people who don't know the language can transcribe it. What is the agreement?
Yeah, but they could be like equally wrong.
They can be equally wrong, Sure, but it's still not well, equally wrong. It's okay in this case because it means that interpretively sounds the same way, right? That's. But I'm thinking about different experiment. Maybe somebody can help me with this. So if you once I talked to an Indian friend of mine in Czech, reduce it, have to check to see how many phonemes you can write once or twice, right, or at least once. But think about it. This is a very good question. Whoever asked that, we don't know how good people are and how much language model they are using, because indeed lip readers are excellent too. However, so it's not that they are not getting any data. And a good lip reader told me that I have an accent in English. So, there is something to it. I am harder to understand because I have an accent. But he didn't know that actually.
I mean, people are really opportunistic. They are very good at judging which information sources are most reliable and exploiting those as best they can. And that's a capability that we really don't know how to do in automatic systems yet.
That's a very good point. It's like definitely the strategies are changing. And you notice it yourself. If you go to noisy environment, you don't explicitly right. So you change the strategy.
Okay, well, thanks for your attention.